Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we explore section 5.5 in the Big Ideas Math Integrated Math 2 textbook on permutations and combinations. Things are about to get a little dicey here because almost everything should be a word problem now, and I think even here I'm not going to say messing up, but having a lot more inner dialogue and conversation and saying, oh, which one is it and why and what do we do? This is where problems can get definitely different as far as what we're doing. And not everything here is probability. There are a lot of things with just respect to arrangements, and you'll kind of understand that phrasing when we see what permutations and combinations are. So before you really step on inside, make sure you strap in and grab your calculator and check the description section down below with the PDF that corresponds with this thing, as well as the timestamps for the problems that I do following the lecture. Let's go ahead and take a look at what we're doing here. We're going to use the formula for the number of permutations and combinations. It's okay if you don't know what they mean just yet. We're going to dive right into those. And, oh, by the way, n factorial. Yeah, I forgot. You might not know what factorial actually means. And now that I think about it, because I haven't explored this section yet, now that I think about it, they'll give you a formula, I'm sure, but I wonder how often they want us to use the calculator versus not use the calculator on these things, because a lot of these can be calculator free with some exception, and you'll see what I mean when we do them, assuming they do it that way. Fundamental counting principle applies before that. We'll see exactly how we want to talk about that. Okay, a permutation is an arrangement of objects in which order is important. The way that I tend to say this phrasing is order matters. Order matters. For instance, the 6 possible permutations of the letters A, B, and C are shown here. When we say order matters, what we mean is using just the 3 letters A, B, and C, and I guess I don't want to dive too much into my combination talk, but using just the letters A, B, and C, there's only one way that you can see letters A, B, and C out of the whole alphabet. But if you switch the order around, it changes the way that it appears, and that's an example of a permutation. ABC, ACB, BAC, BCA, CAB, and CBA are all different permutations of using those 3 letters. That's 6 possible ways, 1, 2, 3, 4, 5, and 6 ways that you can arrange those letters. So counting permutations, let's see an example of exactly this and kind of how it's done, what they're doing there. Consider the number of permutations of the letters in the word July, and they are unique letters. In how many ways can you arrange all the letters and just 2 of the letters? So part A, all of the letters. We use something called the fundamental counting principle to find the number of permutations of the letters in the word July. There's also a kind of a formula, but this works just as well. Number of permutations. There are 4 choices for the first letter. See, you could start with any of the letters J, U, L, or Y to begin with. That's 4 different choices. After you've made your first choice, this kind of sounds like the dependent scenario. After that first choice is made, now there are only 3 choices left for that second letter. If I use the letter U to begin with, after that, U can't be used. Only J, L, or Y can be used, but there are 3 different possibilities. And then 2 different possibilities for the third choice after 2 of them are used. Is that? And then there's only 1 letter left for the last choice. So times 1 doesn't change the result, but you get 24 different ways you can arrange them. Now, I'm not going to give you all those different arrangements, but just that idea is, J, U, L, Y is one of them. But what if you flip the Y and the L like that? Notice that J is the first letter being used. I'll do all the 6 different ways you can do the first letter. As J. J, L, U, Y. I don't know why my color just changed there. Sorry about that. Whatever. And then J, L, Y, U. Notice that you're just doing the different versions of doing U, Y, and Y, U switched around now. And then J, let's see, I use L. J, Y, U, L, and J, Y, L, U. These are the 6 different ways you can arrange July just with J as the first letter. Then imagine there's 6 other ways you can do it with U as the first letter, and 6 with L as the first letter, and 6 with Y as the first letter, just rearranging everything. That's where the 24 kind of comes from and how we do that. The 4 different ways we can do something, that kind of idea. Anyway, when arranging 2 letters of the word July, you have 4 choices for the first and 3 for the second. We're not caring about the different ways you can arrange the last 2 letters, but I can use any of J, U, L, Y to begin with, and after I use 1, then I can just use any of the 3 letters after that. 4 times 3 is 12. So these are ways we talk about the fundamental counting principle. And there are formulas, like I said, that we can use for permutations as well, that I'm sure we're going to dive into in a moment. I see this as monitoring progress, so let's see if this is what I'm supposed to read below. I think so. In example 1a, you evaluated the expression 4 times 3 times 2 times 1. This can be written as 4 with an exclamation mark, but that's read as 4 factorial. Factorial is the way of counting down, I think they're going to say it. For any positive integer n, the product of the integers from 1 to n is called n factorial. I know that can sound confusing, but the way you do the factorial thing, and this can look confusing. So the way that you do that is you multiply your top integer, in this case 4, by every integer below it down to 1, and just keep multiplying them. So 10 factorial is 10 times 9 times 8 times 7, etc., all the way down. And there's a classic case for using these all the time. As a special case, the value of 0 factorial is 1. So it's not 0, it is 1. In example 1b, you found the permutations of 4 objects taken 2 at a time. You can find the number of permutations using the formulas on the next page. Okay, yeah, that's what I kept saying. There are formulas for these things for permutations. We're going to go and take a look at what they are, and they do involve factorial. Okay, formulas. The number of permutations given by n objects is given by n p n, which equals n factorial. So first things first, these are subscripts. Those are like little letters. It's kind of like the opposite of a superscript, like an exponent. I'm not saying it means anything like an exponent. I'm just saying it's a small number like that. That's what you're looking at. Second of all, whenever you see p, you're thinking permutation. I tend to use the word pick in favor of that. So I'll say n pick n, like how many different ways you can pick certain things. And I know it's gonna sound kind of specious after we talk about combinations being choose, but I'll say n pick n a lot. So 4 pick 4, 4 pick 2, things like that. I'm still referring to permutations, at least when I say that. I don't know if that's a me thing or if that's a common thing to say, but I definitely do. Now, n factorial is saying, in this case, there are 4 different objects, in this case, 4 different letters in the word July, and the 4 different spaces for which I can arrange those letters is what they're doing. Now, we do see that as 4 factorial in this case. There's that. Now, for any r objects that are taken r at a time, any n objects taken r at a time, if I have 4 letters to choose from, and I pick 2 of them where the order is going to matter, there's a bigger version of that formula in play, which is n factorial over n minus r factorial. So what happens in the n factorial, n is 4 in this case here, so 4 factorial over, and then they have 4 minus 2 factorial on the bottom because that's our n minus r factorial. Now, they start to do some stuff without a calculator with this, which is fine. You know, if I write this out kind of a little more so, this would have been 4 factorial over 2 factorial. And 4 factorial is 4 times 3 times 2 times 1, whereas 2 factorial is 2 times 1. Now, they seem to leave out the times 1s, but they do something else that I would tend to do as well. I might not necessarily do 4 times 3 times 2 times 1, evaluate that, and then 2 times 1 and evaluate that and divide those. I might find a way to divide things early, and they did the same thing. Obviously, the 1s never appeared, but the 2s are duplicates as well. Notice how they just wrote 2 factorial. But anyway, yeah, once there's a repeat of values there, they cancel out the rest of everything that will divide that's identical on top and bottom, and you're just left with 4 times 3 on top, 1 on bottom, you're just left with 12. So, okay, they did write that whole thing, but they did skip this step on the way. So that does work that way, and that does actually also work for the 4 pick 4 version of it. If you imagine 4 pick 4 would have been 4 factorial over 4 minus 4 factorial, like that. 4 factorial is 4 times 3 times 2 times 1, and if you remember, 4 minus 4 is 0, not if you remember that, but 4 minus 4 is 0, and if you remember, 0 factorial is 1. Right? 0 factorial gives you 1. And that's also giving you the 24 in that same way. So it still agrees. Okay, oh, and look at this. Using a graphing calculator. Yes, most graphing calculators can calculate permutations. And let me show you on mine where it is. I know you might not be using a graphing calculator. I think scientific calculators can also use the same thing, but you can guarantee I'm going to want to use this at some point. So in my graphing calculator here, first of all, you'd have to pick your number first, like 4. And then for mine, I have this math option, and over this probability section, I can find this one, NPR, and we're also going to use this NCR, and you can see factorials there as well. So if I wanted to do 4 pick 2, like that, I compute it, and it does that. And you go like, oh, that's much easier. I mean, we're going to have to know the formula, and I think that that's an important aspect that they're saying that as a side note. And if they're, whoopsie, and if they're saying that as a side note, then to me that means, yeah, we're not going to over rely on that. We're going to do things for ourselves for the most part. So knowing this formula will be kind of important. Is there a way you can remember it? I mean, I know it. I don't know, but there's going to be another one as well for combinations. So, which is going to look like it, but there's a little bit more to it. So I think you're going to know them, but at some point you're going to have to ask which one is which, really. I can see this as being a longer lecture since we're still in permutation. So here we go. Using a permutations formula. 10 horses are running a race. In how many different ways can the horses finish first, second, and third? So yeah, see, now we really want to use the formula. We don't want to get too deep into like, let's write out the different, here's horse A, B, and C, and now let's arrange them, and now let's throw in horse D and horse G. We really want to get into using that formula here. So there are 10 spots for which a horse can finish in the race. There are 3 different places for which we're looking at first, second, and third, and there are 10 different horses that can place in there. Sorry if I said 10 spots. There are 3 spots, and there are 10 horses that can fit in there. So, like I said, you can have ABC or ABD, ABE, FG, HJ, and then you can put ACD. There are a lot of different ways to write it out, but here's how we use that. 10, pick 3. Find the number of permutations of 3 horses chosen from 10. So, 10 factorial over 10 minus 3 factorial. Notice how they work that out as 10 minus 7 factorial, and they kind of cancel out the 7 factorial on top and bottom. Remember, 7 factorial does mean 7 times 6 times 5 times 4 times 3 times 2 times 1. So why write it out if that's going to just appear on top and bottom and they're just going to cancel? Eventually we just do 10 times 9 times 8. 9 times 8 is 72, times 10 is 720. So it's a lot of math you can kind of do on your own, even if you don't have that formula in your calculator. Or you can use your calculator to work 10 times 9 times 8, but you don't have to use that formula to make it happen. So, hey, there are 720 different ways for the horses to finish first, second, and third, meaning the probability of selecting that is 1 out of 720. Well, actually, listen, we're going to get into that right now. I didn't realize it's a probability chapter. So, yeah. Find a probability using permutations, which is the reason why I'm sure they're not going to ask it, but like March Madness brackets, how many different ways? What's the probability of getting the exact bracket right? I mean, it's very little. For a town parade, you will ride on a float with your soccer team. There are 12 floats in the parade, and their order, let me move myself, and their order is chosen at random. Find the probability your float is first, and the float with the school chorus is second. So that's very specific different things that you have. Hold on. You'll ride on a float with your soccer team. There are 12 floats in the parade, and their order is chosen at random. Your float is first, and the float with the school chorus is second. So we're looking at a very specific version of you guys being first and them being second. But here's what they're going to say. Write the number of possible outcomes. That's the number of permutations of the 12 floats in the parade. That's 12 factorial, right? You or the school chorus or any of the other 12 can be chosen first. And then there are 11 slots to be chosen second, and then 10 to be chosen third, etc. So 12 factorial kind of goes on the bottom, right? Now, you write the number of favorable outcomes as the number of permutations of the other floats, given that soccer team is first and you're second. So the way that I'm thinking about that, and I'm probably going to do this because I'm more of a practical, hands-on kind of guy for this. This is what I said. I'm going to have inner dialogue a lot. How many different ways can you be first specifically? And this is order mattering. And the school chorus being second. That's you, 1, and them, 1. Only you slotting yourselves first and you slotting school chorus first. After that, there are 10 different groups that can be chosen here because, right, there were 12 to begin with. So you choose yourself first, you choose them second, and then 10, and then 9, and then 8, etc. And it keeps going. So basically, it becomes 1 times 1 times 10 factorial or 10 factorial. So they're saying, how does that come up? Write the number of favorable outcomes as the number of permutations of the other floats, given the soccer team is first and the chorus is second. So given that you're first and the chorus is second, then it's 10 factorial the rest of the way here because it's 10, pick 10. So you might see me do this a couple times here. I think that it's just a way for me to understand my own outcomes, but it's still a permutation all the same. So the reason why we say favorable outcomes there is because we're trying to say how many different ways can you arrange you guys being first and them being second. You might say one different way, but all the other different folks can be arranged. All the other different floats can be arranged in all these different ways as well. This is out of how many different ways can everybody be arranged as a whole. So that's the long of it. And then 10 factorial over 12 factorial, you can see where these things cancel out. That means that there's still a 1 on top, and 1 over 12 times 11 is 1 over 32. You could have also done a condensed way of this of just looking at the first two slots and saying how many different ways can you guys be arranged as the first two slots in this specific way. That's 1. Out of how many different ways can we have arranged anyone in those first two slots? 12 could have been arranged in the first slot, and 11 after that could be arranged in the second slot. That also gives you the 1 over 132. But that didn't do permutations, and I'm going to be straight with you right now. I don't think I'm always going to show it everything as permutations. So that's why I'm showing all these other versions of it, because I intend on doing anything to the way that I make most sense of, and I hope that you guys can as well when we talk about it. Okay. It's a couple what ifs. All right, let's talk about combinations. And yes, like I said, larger lecture looming for sure. 16 minutes in. A combination is a selection of objects in which the order is not important. So, before I said order matters for permutation, for combination, I say order doesn't matter. So, same thing as that. For instance, in a drawing for 3 identical prizes, you would use combinations because the order of the winners would not matter. Yeah, first person to receive this kazoo, second person received the kazoo, third person received the kazoo. If I swap the first and third person to receive the kazoo, we still got that kazoo, you know what I'm saying? So order doesn't matter. So I think a lot of the questions here are just going to be about, you have to decide, is it a permutation or a combination? If prizes were different, then you'd use permutations because the order would matter. Yes, of course. But a kazoo is the same for each of you guys. All right, count the possible combinations of 2 letters chosen from the list A, B, C, D. Okay, so I really like what they do here because they really spell it out for you before you dive into formula. They show all the different ways you can arrange letters A, B, C, D where order seems to matter. But look how they cross out the duplicates after that. They cross out CA because AC was already used. If you rearrange them, then that's showing order mattering. We don't want order to matter, meaning if you chose the letters C and A, or A and C, regardless of which order that they're provided, it's still one different arrangement of those letters. Kazoo and kazoo. Swap them. Doesn't matter. So they cross out B and A because AB is there, etc., etc. DB, they showed it right here. BD and DB are the same pair, in essence, when they want it to be, right? Count the possible combination of the 2 letters. So there's 6 in total. There's 6 in total. And clearly if permutations had a formula of, in this case, would have been 4 pick 2, 4 in permutation 2, clearly there's one for combinations of 4 choose 2, as I'd call it. So I'm sure that's going to show up. Yeah, right here. In example 4, you found the number of combinations of objects by making an organized list. You can also find the number of combinations using the following formula. So you saw the formula before for permutations as n factorial over n minus r factorial, like this. Sorry, that was for permutations. Combinations includes an extra little set in the denominator dividing by r factorial. Now, I tend to write that first. So if you ever see me write it, I'm going to say n factorial over r factorial times n minus r factorial. You just can't stop habits from forming the way that they are. With me being fully aware that they write it the other way, you'll see me probably write it this way. That being said, the reason the r factorial is in here is because you're dividing out the number of arrangements that would essentially be duplicates. In the case of, this one, perfect. In the case of 4, choose 2. A, B, C, D, and choose 2 of them, where order doesn't matter. The r factorial, the 2 factorial, which is the number 2, by the way, 2, you're dividing all the duplicates that are there, and the duplicates there are doubled up in that case. So you're dividing the doubling up of the ways that I could switch any of these 2 letters, and you can see that we're taking out CB with BC and BA with AB, so we're dividing it by 2. So instead of being 12 different ways you can arrange it, it ends up being 6 as they do the formula the rest of the way. 4 minus 2 is 2, 2 factorial cancel, 2 factorial is 2 times 1, 4 times 3 is 12, divided by 2 times 1, 2 is 6. Whew. And like I said, the calculator also has the NCR, which is the N choose R, the way that I'm going to say it out loud. All right, using a combinations formula. You order a sandwich at a restaurant. You can choose 2 side dishes from a list of 8. How many combinations of side dishes are possible? Yeah, whether you get chips and drink, whatever they're talking about. Whatever. I'm not thinking about that really. But it doesn't matter if it's chips or drink or chips. You still get those side dishes, right? It's the same combination. So order doesn't matter there. So to find the number of combinations, we do 8, choose 2. 8 different side dishes, choose 2 of them. order not mattering, and we plug it in right there. So look how they do this one more time. 8 factorial would have been 8 times 7 times 6 times 5, etc. But because 6 factorial was going to be present here, we can just go all the way to 6 factorial and then cancel those guys out as they do, and then 2 factorial can still be present. Now, I even still here would do 8 divided by 2 is 4 over 1, and 4 times 7 is 28, and 1 times 1 is 1. So 28 over 1, there are 28 different combinations of side dishes you can order. And they also do H2 right here. It's a double check, but it looks like they are very, very intent on using this as often as they can. Okay, finding a probability using combinations. A yearbook editor has selected 14 photos, including one of you and one of your friend, to use in a collage for the yearbook. The photos are placed at random. There's room for 2 photos at the top of the page. What's the probability your photo, and your friend's photo are the 2 placed at the top of the page? So 14 photos to select from, you and your friend are included. So we first come up with the number of possible outcomes as the number of combinations for 14 photos taken 2 at a time. We're talking about how many different ways can the top photos be of anybody. In general, 14 photos, choose 2 specific ones. That's what we're doing 14 choose 2 to begin with. And it ends up being 91. So that's the out of how many in total. Now, how many different ways can you and your friend be at the top? You might say 2 because you say, I can be here, my friend can be there, or I can swap us. But remember, this is a combination case. It doesn't matter if you are here, your friend is here, or swap. That's still you and your friend. Order doesn't matter. This is a combination. In some ways, it's 2 choose 2. And 2 choose 2, if you work out the formula, 2 choose 2 is 1. There's only 1 of the possible combinations, including your photo and your friend's photo. Only 1 out of the 91 different ways they can be arranged. And remember, arranging order doesn't matter, but the 2 photos that are in there matter. So 1 out of 91 is that one. It doesn't seem like they wrote a percentage, and I feel like we're probably not going to write many percentages. We probably have to do the fraction because there are going to be some big ones that might be like 1 out of a million, right? We talk about the March Madness bracket thing, and I'm not trying to figure out what that is right now, but it's, 1 out of forever. So 0.000002% is not something we're inclined on writing. All right, guys. We're going to dive into the problem set, and this is a bigger problem set, and that was a longer lecture, being about 22 minutes in length there. Now, with this problem set, I believe they're up to 58 problems, so I feel like, I haven't looked at the problem set, but I feel like a lot of them are going to be more of just practicing your arrangement of combination and permutation, or choosing what's a combination and permutation to make it a little faster, hopefully, because we're doubling up pretty much the number of problems we've had in the past, or tripling, and don't want to be here for 3 hours. All right, so let's start with the vocabulary and core concept check. An arrangement of objects in which order is important, order matters, is called a permutation. That's called a permutation in which order matters. The other one where order does not matter is known as combination. Which expression does not belong with the other 3? Explain your reasoning. 7 factorial over 2 factorial, 5 factorial. In the case of 2 factorial, I'm going to rewrite that as 7 minus 5 factorial to refer to that as a version of NCR. This is the formula for N choose R. That's 7 choose 5. So this one is some part A, 7 choose 5. And B is literally 7 choose 5. Excuse me. That's the second option is literally 7 choose 5. So that's also the same thing as A. Now, 7 choose 2, you might say that's different, but if you look at the formula and what happens, and I know there's symmetry into this, that's 7 factorial over 2 factorial times 7 minus 2 factorial. And 7 minus 2 is 5. So you still get 7 factorial over 2 factorial times 5 factorial, in which case it's the same thing as that, which means this one must be the different one. Because this is 7 factorial over just 5 factorial, which looks like 7 pick 5. Wait, no, 7 pick 2, rather. That's 7 pick 2. Which is permutation. That means that one's different from the others. It'll be a different result in what you do. So how am I reasoning with it? I'm showing the math, but these 3 are combinations, and that one's a permutation. So combinations, either as the formula or as the way that it appears in syntax, and permutation. Okay. All right, guys, so let's start with the problem set. It should be a doozy. I'm ready for it if you're game. 3 to 58, I believe, on combinations and permutations. Okay, and again, number 1, have your calculator. Number 2, I'll probably do things differently than they might expect me to. They probably want everything to show up as a combination permutation, but I've already kind of shown different ways that I can arrange things and talk about the logic of the order, and I'll probably lean to that as often as I can. I'm not perfect on this stuff. I might even get things wrong. I hope not. I hope my discussion will lead me into it, and I'll pause if I have to think about it, because I want to get them correct for you. But just kind of be prepared for anything on that. In exercises numbers 3 through 8, find the number of ways you can arrange all the letters and 2 of the letters in the given word. Now, on number 3, with using the word at, there are only 2 letters in it, so parts A and B should really be the same thing. For part A, the different ways you can arrange them, meaning order mattering, is going to be 2 factorial, 2 times 1, and I believe, and I don't know if I'm allowed to just go straight into saying factorial, because maybe the example things didn't show the word factorial yet. I forget if they did. But yeah, I think we can. Whereas here, it's still 2 factorial because it's 2 pick 2 in this case. I'll just go ahead and, that's 2 factorial over 0 factorial. I'm not going to get too deep into those. That's 2 over 1, which is 2 as well. Because there are only 2 letters from it, it'll be the exact same arrangement, obviously. AT or TA. I should have just said that. Those are the 2 different ways you can do it. Number 4, try. Now, try is just like the ABC from the example version. There are 3 unique letters, and we're going to find the 3 different arrangements. Just so I can write them out this one time, it's TRY, TYR, RTY, RYT, and YTR, and YRT. There's 6 different ways you can arrange them, and that will be 3 factorial, because there are 3 ways you can choose the first slot, and then 2 ways you can choose the second slot, and 1 way you can choose the last slot. After that, 3 times 2 times 1 is what we're doing there. That's where you get 6. Now, in the next case, we want to choose 2 different slots, the first 2 slots. That's where we're going to do, and I might just show this way as well. I want to show all different combinations, all different ways you can look at these problems. 3 different ways to choose the first slot, 2 different ways you can choose the second slot. And that still gives you just 6 right there. Because take a look, it's these ones right here, right? Are all these unique? TR, TY, RT, RY, YT, YR. Yes, they're all unique, and order does matter in this case, so it's still 6 in that case for a different reason, though. You're like, is everything going to be the same always? 2, 2, 6, 6? No, no. As we expand the number of letters, and you can tell, I didn't notice, but that's what we're going to do. First it's 2 letters, then 3, 4, 5, 6, and 7. As we expand, it's going to kind of show differently, probably starting now, in a unique sense. So the word rock, R-O-C-K. So for part A, there are 4, I'm going to show it this way this time, 4 factorial, 4 different ways you can choose the first letter. After that, you've chosen a first letter, it depends on it. Then there are 3 different ways to choose the second letter, 2 ways to choose the third letter, and then there's just 1 last letter you can choose after that. That's where you 4 times 3 times 2 times 1, and that'll give you 24. At some point, I think you're going to remember some of these numbers, the factorials, maybe. Anyway, the next thing is going to be a 4 pick 2 scenario. 4 pick 2 because there are 2 different slots. Really, it's just going to be 4 times 3. It's just going to be 4 times 3, but let's try it with this permutation way. That's 4 factorial over 4 minus 2 factorial, which is 4 factorial over 2 factorial, which we just saw 4 factorial is 24, and 2 factorial is 2, which gives you 12. 12 different ways you can arrange just the first 2 letters in, not the first 2 letters, but 2 spaces, 2 of the letters in the word rock. Number 6, we have the word water. You might notice it doesn't matter what the actual word is, as long as the letters are unique, and as long as they're not asking you specific things about the word, like not where the order matters, but that it's alphabetical, or that you're talking about only vowels, or something like that. But the word itself hasn't mattered in my calculations. I hope you're understanding that. So this one's going to be a 5 factorial case, given that they're all unique things, and it looks like they will always be unique in these options. They haven't talked about it otherwise. So that's 5 times 4 times 3 times 2 times 1, or 5 times 4 factorial. I bring that up because we already saw what 4 times 3 times 2 times 1 was. 5 times 24, which is 120. And that's another way you can learn some of these really fast. Right? What's 6 factorial? It's 6 times 5 factorial, 6 times 120. So we're going to answer that one actually next after this. Part B, the first 2 letters, we're really just looking at that 5 times 4 scenario. Let me write it though as, I do want to show this. 5 pick 2 is 5 factorial over what would be 5 minus 2 factorial, 3 factorial. So that's 5 times 4 times 3 factorial over 3 factorial. You don't have to write 3 times 2 times 1 if you think it's just going to get in the way of what we do. And you might spell it out more when we're doing combinations. It all depends. But that becomes just 20. 20 different ways to do that. It's growing more than the previous one, but it's really separating itself when you're just talking about the two of the letters to choose. Number 7, family. Let's kind of go a little faster now that we've recognized what's happening. So for the word family, 6 letters. That'll be 6 factorial. Now it'll just be the same with these. 6 factorial is going to be 6 times 5 factorial. You could also use your calculator, but 6 times 120 in that case is 720. Now, if number 7 was the first problem you did, you're probably wondering where I got the 120. I'm not going to answer that. You should have had the other problems before it. Part B, I'm just looking at 6 times 5, and I feel like I'm going to do a lot of these slots more often. When we hit word problems, I'm really going to talk about it in this kind of way. I'm probably not going to say permutation is often there. It depends. It depends. Number 8, flowers. Now we're talking about 8 factorial. 7. Flowers is 7 letters. I saw number 8. Flowers. I'm thinking my cousin Vinny. And flowers. 7 factorial. I actually don't know that one. Let me actually just jump to the calculator for this one. I know it's 7 times 720, but let me jump to this one just to show you where that factorial option is. So 7, and I'm going into math and going to option 4. 7 factorial is right there. This is 720 times 7, which is 5040. So that is that guy. Now the second one will be significantly easier to work off of. Let's just do the 7 factorial over 7 minus 2 factorial. 7 times 6 times 5 factorial over 5 factorial. That's where 7 times 6 is coming from. That's where we get 42. And there we go. Okay, evaluate the expressions here on numbers 9 through 16. And now I kind of feel like we were supposed to probably save permutations for now, but that's okay. Now that we've seen a bunch of them, I feel like this is going to go significantly faster. So 5 pick 2 is 5 factorial over 5 minus 2 factorial. Yeah, I do feel like I jumped the gun a little bit. My bad. 5 factorial over 3 factorial. So that's 5 times 4 times 3 factorial over 3 factorial. And as those are gone, you have 5 times 4, which is 20. 20. I will, because there are 8 of these problems, I will speed up what I do over time. Let me show one version of that speed up. And at some point, I think it's going to be kind of uber fast. Because I kind of hope you catch on, right? By the point that we're finished with this set, I want to use them in word problems because I think those are coming next. I see 17 and 18. They're word problems where we want to understand the crux of the word problem more than what we're calculating because we have a calculator to do some of these if we have to. This is 7 factorial over 7 minus 3 factorial, which is 4 factorial. 7 times 6 times 5 times 4 factorial over 4 factorial gives you 7 times 6 times 5. Now 6 times 5 is 30 times 7 is 210. You can see that I'd rather do 30 times 7 than 42 times 5 or 35 times 6. So there's a strategic way of going about what you want to calculate and how, and that was my choice for that one. Let's go to number 11. Number 11 is 9 pick 1. There are 9 different objects to choose from, and you have 1 slot to choose them in. How many different ways can you do that? I think 9, but if you weren't certain, let's try 9 factorial over 9 minus 1 factorial, 8 factorial. That's 9 times 8 factorial over 8 factorial. If you notice, that bottom guy is just canceling out each time. You are left with just the thing that's left on top after. So let's try that for this next one on number 12, 6 pick 5, where what I'm going to do, 6 pick 5, that's 6 factorial over 6 minus 5 factorial. Oh, I guess this one is, well, 1 factorial is 1, but, okay, so this is 6 times 5 times 4 times 3 times 2. What I wanted to show, though, was that, first of all, times 1 doesn't need to be written anytime we have it, but even if it was a 10 factorial here, if 10 factorial was on bottom, I'd cancel them out. So we saw 6 factorial before, that was 720. And that's really what's happening there. 720 different ways that you can get those arrangements when order matters. If order doesn't matter, it's going to be a significantly different number. Significantly smaller number. Number 13, 8 pick 6. Now that we have 4 more to do here. It's 8 factorial over, not 6 factorial. Keep in mind, it is 2 factorial. So we're going to divide the whole thing by 2. Or 2 factorial. I think at that point we can just kind of leave that part out, right? The 2 times 1 is gone. So let's do this. And let's see if there's a way I can do this. I'll do it without a calculator, but I can do it cleanly. For example, 6 times 5 is 30. I like that one. Times 4 is 120. Times 3 is 360. I got 360. Oh, this won't be that clean, I guess. Times 8 times 7 times 56. Oh boy, maybe I should have found a different way to do that. Yeah, let me go to the calculator. 360 times 56. 20,160. Some point you just got to use a calculator. All right, number 14. 12 pick 0. Okay, let's think of it logically first. You have 12 different objects, and we're going to choose none of them. How many different ways can you choose none of them? Don't say 0. There's one way you can choose none of them by not choosing any of them. So let's look at 12 pick 0. That's 12 factorial over 12 minus 0 factorial, right? So that's 12 factorial over 12 factorial. Anything divided by itself, any non-zero number divided by itself, which this is. It's not that these cancel, right? Because otherwise some people will say 0. They'll say there's nothing. No, that's 1. Any non-zero number divided by itself is 1. There's one way that I cannot choose anything. That's by not choosing them. There you have it. Number 15, 30 pick 2. I'm glad it's 30 pick 2 and not 30 pick 28. But 30 pick 2 is going to be 30 factorial over 28 factorial, which means we're really just doing 30 times 29. If we go back to our original kinds of problems, this is a 30-letter word with all unique letters, which is impossible now that I think about it. And we're choosing the first 2 slots, 30 times 29, right? That's where that works out. 870. 870, I believe. Number 16. Yeah, these fly a little faster to begin with. Let's hope it kind of stays on that pace. Word problems, be darned. 25 pick 5. So we got 25 factorial over 20 factorial. That means we got to do 25 times 24 times 23 times 22 times 21. The 20 factorial after that's going to just kind of not be there. Probably can't do a lot of that in my head, the way that I want to. So I'm going to leave it to the calculator. You know what? I will actually do in the calculator this time. I will show that, but I'm also going to show the, because this number's pretty big, I imagine. 6 million? 637, yeah, 6,375,600. So 6375600. What I'm also going to do is show you 25 pick 5. 25 pick 5. Because I'm going to do a lot of these later, I'm sure, now that we've kind of worked out the formula. At some point, I kind of abandon the formula in favor of the calculator if I really feel like it's just the way to go. So that's going to be the same answer, as you can tell. Number 16. Okay. Let's go to number 17. 11 students are competing in an art contest. In how many different ways can the students finish first, second, and third? Now, listen, we haven't, dove in. We haven't dived into combinations yet, so I think we can clearly tell that this is a permutation problem just by nature of the structure of the problem set. However, does it make sense that it's a permutation? And how many different ways can students finish first, second, and third? Order matters. If I finish first, you finish second, and Bob finishes third, that's different from Bob finishing first, you finishing second, and me finishing third. Order matters. This is still a permutation. There are 11 students, and we are going to pick 3 of them for the top bill. As you can tell, this is 11 times 10 times 9. There are 11 different ways. It says students can finish first, second, third. It's not just me, you, and Bob. There are 11 different students that could finish first place, 10 different that could finish second place after the first one's chosen, and then 9 after that. So that's kind of where that's, coming from. Let's see. 99 times 10 is 990. 990 ways. And I feel like now that it's a word problem, I have to have units, and my units will now say ways. We'll see if I maintain that. I'll probably forget right now. Number 18. 6 friends go to a movie theater, and how many different ways can they sit together in a row of 6 empty seats? So kind of just arranging all those, 6, right? So 6 friends, 6 different seats. So 6 pick 6. We're talking about a 6 factorial case, right? I can be in this first seat, or any of the other 5 people, right? We've seen 6 factorial several times, so I'm just going to write it like that. But really, once again, that's 6 different people can choose this first seat, and then after that, that's 5, and then 4, etc., times 3, times 2, times 1. Jeez, I'm not doing normally I do the underlined parts first, and then I write in the numbers after that, but 720 ways. All right, number 19. You and your friend are 2 of 8 servers working in a shift at a restaurant. At the beginning of the shift, the manager randomly assigns 1 section to each server. Find the probability you are assigned in section 1 and your friend is assigned in section 2. So this is one where I might work more of the logical aspects of this thing, and that is very specific in how they're arranging these things. So 2 of 8 servers working a shift means that at the beginning of the shift, manager randomly sends 1 section each server. Find the probability you're assigned section 1, specifically section 1. How many different ways can you be in specifically section 1, just you as that one way? How many different ways can your one friend be assigned to section 2? Your friend is just one way. Now, they're talking about probability here. So in this case, what we're also looking at are all the different ways that other people can be assigned the different sections, the other 8 of them. That's 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial. I'll write this one out the first time. If there's another problem like this, I'll kind of change it up. So it's like that out of how many different ways could any of you guys been arranged in those 8 different things? Well, there are 8 different people that could have been chosen in section 1 as an overall, just not as a desirable outcome. And then it goes the rest of the way, 6, 5, 4, 3, 2, 1, where this is going to eventually cancel itself out, but you are looking at a 1 out of 56 probability. And like I said, I'm not going to dive into percentages unless they really feel like the percentages are the way to go about that thing. But since these numbers are going to be so small, that's less than 2%, and that's probably a bigger of the numbers, I'm not really going to go ahead and use that. So as a different formula thing that we'd be talking about here, on the top, there's a 6 pick 6 going on because after you and your friend are arranged, there are this many ways to do that set. And there's 8 pick 8 on the bottom there to kind of work that out as well. And so that's something you can do, which is 6 factorial over 8 factorial. Okay, let's go to number 20. You're making 6 posters to hold up at a basketball game. Each poster has a letter of the word Tigers, all unique letters. You and 5 friends sit next to each other in a row. The posters are distributed at random. Find the probability that Tigers is spelled correctly when you hold up the posters. There's only one way you can spell out Tigers correctly. Tigers, right? Otherwise, you can see something like that. Go Griste. Something like that, right? A lot of different ways you can do that. How many? 6 factorial. There are 6 letters, and there are, 6 slots in the first thing, etc. So that'll be 1 out of 720. The classic 720 value that you have right there. 1 out of 720 is going to be that one. So you can see just how these things can be arranged in such different ways. That's a little much. It's a little much as an overall. Griste. All right, exercises 21 to 24. Count the possible combinations of R letters chosen from the given list. So now we're hitting combinations instead of permutations. Order does not matter in this case. We have formulas to be arranged here, and we can talk logically about some of them if we have to. Count the possible combinations of R. I feel like they don't want us to use the formula yet. And I wonder if we were supposed to do that or not for permutations. Thankfully, combinations tend to be a smaller number of things. So with A, B, C, D, and we can choose 3 of the letters. Let's write out what those options are. There's A, B, C. There's A, B, D. There's B, C, D. There's hold on. B, A, D. Hold on. A, no, we already have that. I want to make sure there's nothing else. This might be it. I feel like there are more, and I'm not thinking of them right now. Remember, order doesn't matter in this case though, because you're like, wait, hold on, what about CBA? You know, things like that. No, that's the same thing as ABC, right? Same with BCA, same with ACB, stuff like that. So all these are different. Anyway, there might be 3 different ways: ABC, ABD, and BCD. So let's. I think there's a 4th. I don't know why I'm not. Oh, ACD. I'm like, hold on. There can't just be 3. So 4. There are 4 different ways that you can do that. I'm like, what am I missing? Something didn't feel right. Because I knew beforehand the answer was supposed to be 4 because of what it is. And I was like, what am I missing? Anyway. 4 different ways. Sorry about that. I'm not going to write out all of them and cross out all the different things that are duplicates. But I wanted to get those out. All right, number 22, LMNO, where R is 2. So there's LM, LN, LO. It's easier when there are 2 letters for me to do this. There's MN, MO, and there's NO. Any rearranging of these by switching them will not count. So there's 6 different ways for this one here. And it's easier for me to do that one because I'm looking at L with M, N, and O. You know, I'm kind of like moving that slot around like that. Boom, boom. And now I've used everything that used L. So then I go M with N and O, and then N with O. That's kind of how I wrote that out. Number 23. See, now, I don't know if they want me to actually arrange them this way or if I'm allowed to use the formula basis for it. Because when they say evaluate the expression afterward, I feel like we're supposed to use the things there. You know what I do want to do with all these problems, though, is copy down the thing. A, B, C, D, where R equals 3. Sorry about that. And then L, M, N, O, where R equals 2. And then this one is U, V, W, X, Y, Z, where R equals 3. Okay. Yeah, I feel like I'm going to spell these ones out. I think the whole point is to make sense of what it is you're doing before the formula is used. So here's how I'm going to do this. I'm going to put U and V as the first 2 letters, and then I'm going to put in W, X, Y, and Z. U, V, W, and then U, V, X, U, V, Y, U, V, Z. After that, I'm not going to pair up U with V anymore. Now I'll pair up, say, U with W. U with W with then X, Y, and Z. And then I'll pair up U with X, and then have Y and Z. And then U with Y with Z. See, you won't say, well, why didn't you do UXV? Because I already have UVX right there. Orders matters. That's 12 different ways for that. From that set with U as a letter. Now let's go to V. V as the beginning letter. And then I have W with X. V, W, Y. V, WZ. And I know this might seem like a lot to write. Trust me, I've written a lot more for earlier. If you remember section 5.1 or 5.2, whichever one it was, trust me, I've done a lot more than this. This is going to shrink up over time, and maybe you'll start to see a pattern. In fact, you might already start to see the pattern if you notice this. That's going to happen here. Notice that this is going to have 3 right there. Now I'm going to put V with X, VXY, VXZ, and then VYZ is the last set there. So that had 3 different sets. Now I go to W, it's going to have that. So check this out. This is going to have, this is 10 plus 6, and then we'll have plus 3 and then plus 1. So 10 plus 6 plus 3, where are the 3 coming from? Using W, fronting with W, WXZ, excuse me, WXY, WXZ, WXY, WXZ, and then WYZ. That's 3. And then just the 1 is XYZ. I know I'm really spacing this out. XYZ hasn't been used yet, and that's 1. Yeah, that's a lot. So 10 plus 6, 16 plus 3 plus 1 is 20. 20 ways. And yes, there's a formula to use all that, but now we've kind of gotten the understanding of what's happening. And then number 24. We have 5 letters chosen 4 ways. This is going to be small. D, E, F, G, H, where r equals 4. So look at the different things we have here. We have D, E, F, G, or D, E, F, H, or not using D at all now, not using E at all. See, I messed up again. D, F, G, H. Now I can't use D at all. E, F, wait, yes I can. Shoot, I keep messing this up. D, E, don't use F. G, H, that's the problem I had the first time. And not use G at all. D, E, F, H. And not using H at all, we already did. So there are those, and then there's E, F, G, H. Hold on, did I do something? I did D, E, F, H twice. I'm sorry, I already did that one. And there's E, F, G, H. So there are 5 different ways you can do that. I think there was a better systematic way I should have talked about that, and I don't realize what it was. I probably would have said keep these the same. It's easier when I have less letters, I'll be honest. So in this case, I could have said take the G and move it over there. I mean, I don't know. There's a bunch of different shifts. Anyway, there are 5 different ways. 5 different ways. It's a smaller set. Whereas if this was rearranging where the order matters, this one is a smaller set when you get closer to the amounts that you're choosing from or closer to 0. Okay, now I'm going to use the formula, guys. Number 25. We're going to do 5 choose 1. Combination of 5 letters there. Now, the formula is n factorial, and n choose r, n factorial over r factorial times n minus r factorial. And I'll spell this out a couple times for you guys. So that's 5 factorial over 1 factorial times 4 factorial. Now, 1 factorial is just 1, so that can kind of just leave itself out. But I got 5 times 4 factorial here over 4 factorial on the bottom. Or 1 times 4 factorial, that's fine. And that's 5. That's 5. There you go. Number 26, we have 8 choose 5. Good thing I'm not spelling out, letters in that case here. But 8 choose 5. There's something they haven't brought up, and I doubt they will. You probably won't hear it till IM3, but there's something else. You can look this up. It's called Pascal's triangle. If you're not sure how to spell Pascal, P-A-S-C-A-L. Pascal is the name of the chameleon in Tangled. But anyway, Pascal's triangle. These combination things also appear in Pascal's triangle. That's a way that I kind of remember some of these numbers. Anyway, this is 8 factorial over 5 factorial times 8 minus 5 factorial. Or 8 factorial over 5 factorial times 3 factorial. So here's what I'm going to do. Eventually I'm going to write this kind of faster later, but 8 times 7 times 6 times 5 factorial is here. You notice 5 factorial is on bottom. And on bottom here I have 3 factorial, which is 3 times 2 times 1. So I get to cross out the 5 factorials. You'll notice that 3 times 2 times 1 is left. Now instead of doing 8 times 7 times 6 on top and then 3 times 2 times 1 on bottom, find things that can reduce early on. Like I can do 6 divided by 3, which is 2. And 8 divided by 2, which is 4. As long as you can see what I still have here, I have 4 times 7 times 2 on top, and on bottom I have 1 times 1 times 1. Well, 4 times 7 is 28, doubled is 56, and 56 over 1 is indeed still 56. So 8 choose 5 is 56. Number 27, and you can verify any of these with a calculator. 27, I have 9 choose 9. I have 9 different things, and I have 9 spaces to arrange them or order. Doesn't matter. I think there's only one way to do that. So that's 9 factorial over 9 factorial times 9 minus 9 factorial, which is 9 factorial over 9 factorial times 0 factorial. 0 factorial is 1. And 9 factorial over 9 factorial is 1. This is 1. There's only one way I can arrange those. Remember, order doesn't matter. All right, number 28, because it looks a lot like 26, I'm going to start my step skipping processes for this and just kind of work it out in ways that can make more sense in streamlining it. This is 8 factorial. First of all, it's 8 factorial over 6 factorial times 8 minus 6 factorial. Boom. If you noticed last time, I can just put 8 times 7 on top if you understand the 6 factorials are going to cancel, and 2 factorial is 2 times 1. 8 divided by 2 is 4, and 4 times 7 is 28. So number 28, awesomely enough, is going to have 28 different combinations for it, which I'm all for. Well, 29 of 29, I was going to say undoubtedly. Doubtful. Doubtedly. Number 29. 12 choose 3. You never know. 12 choose 3. That's 12 factorial over 3 factorial times 12 minus 3 factorial, or 9 factorial. So, that'll be 12 times 11 times 10. 9 factorial is the bust there. 3 times 2 times 1 remains. So let's work things out and shrink them a little bit if we can. I'm going to do 10 over 2 to get 5, and 12 over 3 to get 4. And just 1s exist on bottom. 4 times 5, 20 times 11, 220. I don't know why that took me a while to think about. So that's 220. So hopefully you're kind of understanding that. You know, you can verify any of these with the calculator. I'm not, but you can kind of check and see for yourself if that'll work. Number 30. 11 choose 4. And I think, you know, as I said before, after I do these ones, see, the ones I did before were without the formula. The ones I'm doing now are with the formula. After that, all bets are off in terms of, do I need to use the formula for myself, or can I just use the calculator? It depends on the question. But 11 choose 4 is 11 factorial over 4 factorial times 7 factorial. So on top, we still got 11 times 10 times 9 times 8 before the 7 factorial kicks in. And on bottom, we still got 4 times 3 times 2 times 1. So again, I'll try calculator free. I have a 10 over 2 to give me 5, 8 over 4 to give me 2, and 9 over 3 to give me 3. 1 exists on bottom now. 11 times 5 times 3 times 2 is what remains here. What's the quickest go around? 5 times 2. 5 times 2 is 10. Times 3 is 30. Times 11 is 330. So number 30 is 330 as an answer. Seems like they're really cranking up the numbers, though. So at some point, if a calculator is used, oh well. Number 31. I'll still use the formula, but 15 choose 8. It's 15 factorial over 8 factorial times 15 minus 8, 7. Didn't need the parentheses, my bad. So 15, oh, I'm probably using the calculator this time. 13 times 12 times 11 times 10 times 9. 8 factorial takes hold, and after that, we have 7, 6, 5, 4, 3, 2, 1. The 1 never really truly matters, but I kind of have it there. All right, what's best? 15 over 5. 15 over 5, where we get 3. 14 over 7, where we get 2. 12 over 6, where we get 2. 10 over 2 gives me 5. 9 over 3 gives me 3. And even check this out, right? We can take any of the 2 over 4s. 2 over 4 is 1/2. So I have 2 there. So and 2 over 2 is 1. So I had a 2 times 2 on top, right? So now on bottom I just have 1. Now I just have, let's write this out, 3 times 13 times 11 times 5 times 3. It's very possible I missed something, in which case I'll try this on the calculator as well and see what I get. And I actually don't know this part here. The numbers are too weird. So let's try some of this on the calculator now that I've really played with that a lot. I'm going to do 3 times 13 times 11 times 5 times 3. Let's see if I either missed any numbers when I wrote some things out, or if I miscalculated. Let's do 15 choose 8. 15 choose 8. Oh, good, it's the same number. All right, 6, 4, 3, 5. At some point, calculator usage is appropriate, especially if I did all the work leading up to it kind of fairly. I didn't even notice that we're on questions that we never even hit before. This is the first time we hit a problem in the 30s that I recall. I don't know. And yet, about an hour in. So maybe we are on a good pace going to 58. 20 choose 5. Hopefully this number's a little smaller. 20, or not smaller, but easier to work off of. 20 factorial over 5 factorial times 15 factorial. So we go down to 15, or 16. 20 times 19, 18, 17, 16. The 15 factorial is kind of gone there. And now we got 5 times 4 times 3 times 2 times 1. It is kind of fun to work out some of these reduction things. I know probably you don't care, but I think it's fun. 20 over 5 is 4. 16 over 4 is 4. 18 over 2 is, let's do 18 over 3. 18 over 3 is 6. And 4 over 2 is 2. And 1 is on the bottom. So now I have 4 times 19 times 6 times 17 times 2. Yeah, number's still too weird. I can work out this. 4 times 6 is 24 times 2 is 48. So I have 48 times 19 times 17. But after that, it's... Let's just work it out. 48 times 19 times 17. And I'm getting 15,504. So 15,504. I'm going to trust it. And there you have number 32. Okay, let's go to number 33. It's probably a combination-based question alongside some other word problems after that. Before they trick us up, maybe we haven't hit error analysis even yet. I wonder if that'll show up. I assume error analysis is the next section after some of these word problems for a combination. Each year, 64 golfers participate in a golf tournament. The golfers play in groups of 4. How many groups of 4 golfers are possible? So hopefully you can tell how order doesn't matter here. Whether it's, Andy, Bob, Charlie, and David, or you swap kind of, David, Charlie, Bob, and Andy, that's still that group of 4 golfers. So how many groups of 4 golfers are possible? How many different ways can you arrange a group of 4 golfers out of 64? That's 64 choose 4. Now, I know that you're likely to go to the calculator, and in some cases I would as well, but maybe this number, it might be big, but I think this one we can actually work off pretty well. 4 factorial over 60 factorial. Sorry about the parentheses. 64, 63, 62, 60. I might. In some of these cases, guys, I might use the calculator. I hope you're okay with that. Because 60 factorial is gone. I got 4, 3, 2, 1 here. 64 over 4 is 16. Yeah, this stuff might not play. 63 over 3 is 21. 62 over 2 is 31. Yeah, it's still not a fun number. So I am obviously going to go to the calculator for this one part, but I'm going to confirm that I got the right number. After that, if the numbers are this big, I'm just going to work off of just the combination formula. I think the question is, can you come up with the right formula for it, right? So let's see if I got the right number first of all. I got this many different ways, which is a lot, but it's a lot of golfers. And let's try 64, choose 4 as well. Yeah, same number. So there are 635,376 ways that you can arrange 4 golfers out of 64, where order clearly shouldn't matter. All right, number 34. Oh, look, error analysis is after that. You want to purchase vegetable dip for a party. A grocery store sells 7 different flavors of vegetable dip. You have enough money to purchase 2 flavors. How many combinations of 2 flavors of vegetable dip are possible? Well, now that the numbers are smaller, I think I can work that out. So this is going to be a 7 choose 2 scenario here. 7 different flavors. Order shouldn't matter. The 2 flavors, whatever you're using for dip. Hummus or avocado or whatever. 7 factorial over 2 factorial times 5 factorial will give me 7 times 6 over 2 times 1. That should be 21. 42 over 2. 21 different ways. Oh, the varieties. I shall return every day with a different combination for the entire month. Yes, I shall. Let's get her done. All right, error analysis. Let's see how they mix up combinations, permutations, things like that. I don't know. Okay, I see the problem with the top one. And I think I mentioned this in the last section thing that I did. Normally, I like the error analysis problems because it shows different things that students do that are wrong. So it gives students a different way of looking at what's going on. A lot of students don't make the mistake that you're about to see right here. In fact, I'll show you other mistakes that students do make. But 11 pick 7 being 11 factorial over 11 minus 7. Oh, they're missing the factorial symbol, right? That should have a factorial and that should work itself out. So they're missing the factorial symbol on the bottom. See, I don't think I've ever seen a student do that. So that's something, So let's correct it. 11 pick 7 should be 11 factorial over 11 minus 7 factorial, which is 11 factorial over 4 factorial. Now, I'm not going to get deep into the, I'll let my calculator do that. So let me show you the 11 pick 7 in general. 11 pick 7, or, which is that number, or 11 factorial over 4 factorial. And this is a good time to mention your calculator uses order of operations with factorials before division. So I don't need to wrap 4 factorial in parentheses. In this case here, it's going to do order of operations appropriately. It's not like it's doing 11 divided by 4 first, or 11 factorial divided by 4, and then doing the factorial of that, which is cool. It's like exponents in that way. Anyway, that number is 1663200. Boom, boom, boom. That many different ways that I forget that. Oh, this wasn't a word problem. So I was writing the word ways there, but it should be that instead of the other massive number they had. Now, what's a common mistake students would do? A lot of students will accidentally do 11 factorial over 7 factorial. Right? That makes sense to kind of, hey, those are my two numbers. Like they should be in the answer. So that's a very common thing that occurs, and I'm surprised they didn't show that. Unless they show it on this problem. Nope. In this case, it's a combination question, and they worked it out like a permutation, where they're missing something. But they used the permutation formula for a combination question. There's still another part that's needed here. Now, the way that it's actually written, instead of n factorial, let's see, n choose r, it's not just n factorial over n minus r factorial. That's a part of it, but there's also r factorial that multiplies by it. I know they multiply it last. I multiply it first. I'm going to go ahead and just work out that on the calculator. 9 choose 4. So instead of being 3024, it's actually just 126. So yeah, combinations tend to have lesser arrangements because the order doesn't matter. You're not going to do a swap and boom, there's another arrangement on those. All right, and listen, I think people would make that mistake. And the other big mistake in general is just that you just don't know the formula. Or, whatever, something like that can happen as well. All right, number 37. 37 to 40. Tell whether the question can be answered using permutations or combinations. Explain your reasoning, then answer the question. All right, so we do the which one is it, and then we actually solve it. To complete an exam, you must answer 8 questions from a list of 10 questions. In how many ways can you complete the exam? Not only does order not matter, we don't even really look at order in different ways for this. Right? Well, you might. I'm going to do question 1, then question 2. I'm going to do question 2, then question 1. That's not really completing the exam in a different way. You still did questions 1 and 2. Right? To your teacher, that doesn't matter when you do those. This is a combination because order shouldn't dictate a different arrangement. Order doesn't matter. A different arrangement of questions chosen. So now we still have to do the problem. This is going to be 10 choose 8. There's a list of 10 questions. We choose 8 of them. I don't know. I want to do it in my calculator, but I have to go to the calculator. I have to click buttons, and that takes a while. I feel like this is just as fast. Probably not. 10 times 9 over 2 times 1. That's me 45. There are 45 different ways. If I kind of did all my stuff in my head fast, there are 45 different ways that you can get. You can combine, choose those ones there. All right, number 38. 10 students are auditioning for 3 different roles in a play, and how many ways can 3 roles be filled? Well, this one sounds like a permutation because the roles aren't just extra number 1, 2, and 3, and even if they were, you're doing something very specific. This, it's the lead role, the supporting role, the villain. This is a permutation. Order matters. Order matters because the roles are unique. So, how many different ways can the 3 roles be filled of 10 students auditioning? It'll be a permutation, 10 different slots, 10 different people, and 3 different slots, 10 pick 3. So that's 10 factorial over 7 factorial, or 10 times 9 times 8, which is, we've seen that number before, 720. It's in a different way that it's being arranged, but still 720. Okay, number 39. 52 athletes are competing in a bicycle race. In how many orders can the bicyclists finish first, second, and third? The first, second, and third thing is ranking. Ranking is order mattering. Order mattering is permutation. So it's a permutation. Order and ranking of placement matters. Right? I finished first, you finish second, he finishes third. That's different than me second and whatever. So 52, pick 3. Now, it is a small calculation, 52 times 51 times 50, but I don't want to do it. So I'm going to do 50. I'm going to do this in my calculator. 52, pick 3. 132600. Yeah, I don't know if I would have come up with that, in such a way. All right, number 40. Number 40. An employee at a pet store needs to catch 5 tetras in an aquarium containing 27 tetras. I don't know what tetras are. I'm guessing aquarium. I'm guessing they're fish. In how many groupings can the employee capture 5 tetras? So they're like scoop, like, oh, I got the gold one, the green one, blue, orange, and black. There's no order to that. Rearranging those inside the capturing of them, what'd they say? Catching them. That doesn't matter. This is very much a combination. I'm just going to say order doesn't matter. The question is, does order matter or not? And this is something where you could argue, not for this one really. There are some of them that I understand where we can make an argument whether it's combination or permutation. I think they're being very clear cut and dry in these ones. The question is, what's a tetra? So this is 27, choose 5. And like I said, I'll let my calculator kind of take hold right now. So 27, choose 5 is going to be 80,730. 80730 ways. I don't know if I've been saying ways after in any of these things, but I'm going to that time. Because I can, and I did. Okay, that's number 40. Let's go to number 41, critical thinking. Compare the quantities 50 choose 9 and 50 choose 41 without performing any I know the answer. Explain your reasoning. So this is where combinations kind of do something different from permutations. They said without calculating anything doesn't mean I can't write out a formula. So 50, and we probably want to. 50 choose 9 is going to be 50 factorial over, check this out, it's r factorial times n minus r factorial. Now that is 50 factorial over 9 factorial times 41 factorial. That should be a 1. I hope you know where I'm going with this, or I hope you know where this problem's going. 50 choose 41 is 50 factorial over 41 factorial times 50 minus 41 factorial. And 50 minus 41 is 9. So it's 50 factorial over 41 factorial times 9 factorial. Every time I'm writing 41 factorial, I start writing 4 factorial, so that's whatever. So when we compare these things, look, I'm not calculating them, but multiplication's commutative. Rearrange these things. It doesn't change what the answer is. These are the same. These are the same value. Whatever it is, they are the same. And yes, there's symmetry involved in this. 50 choose 0 and 50 choose 50 are the same number. In that case, that's just 1. And yeah, that's just how that thing works. And there's symmetry in combinations. 50 pick 50, 9 and 50 pick 41 would be different values, however. Okay, number 42, critical thinking. Show that each identity is true for any whole numbers r and n where r is between 0 and n inclusive. Okay. Part A, n choose n equals 1. I forget if they did that part in the lecture. I know they probably did it for I did it for permutations in the lecture. I did not do it for combinations at all, and they didn't. So it's our time. So this, does it equal 1? We got to show that this identity works. So this equals n factorial over n factorial times n minus n factorial. N minus n is 0, and n factorial over n factorial is 1. 0 factorial is 1. So you get 1. So it does agree. It works out. They're saying show that this identity is, they say identity? Yeah, each identity is true here. The r's between 0 and n is important because when we refer to those parts, we need to state that these are going to be integers. But you can't choose more than is possible. If I had 6 different things and I want to choose 8 of them, that's not possible. And we always want to choose a whole number, a positive number, or 0 from our amount. So we're not going to choose negative, and we can't choose more than we have. Not number 43. I need part B. Part B. Part B, we have n choose r. Now, we know the formula, but let's see if it's the same thing as n choose n minus r. So we know that n choose r is n factorial over r factorial times n minus r factorial. And in fact, this goes right to that question before. This is number 41 in a different way. The fact that n minus r is written first, now this is n minus r factorial. And what happens when you subtract n minus r from n minus r factorial like that? That's weird looking, right? But here, this is, actually, let's leave this one as n choose r. I think we just want to show that it ends up looking like the same thing. N choose r on this side, and here we rewrite it. So over here, I'm going to have n factorial over, here's n minus r factorial. N minus, let's just do this. N minus n plus r. I'm distributing the negative, and n minus n cancels out. You're left with r. So that just becomes r factorial there. And yes, that does match up with the formula. Okay, I will write it. N factorial over r factorial times n minus r factorial. And in fact, this is the way they write it in the book. Here's me with my rearrangement. It still checks out. Yes, it's all good. It's all good. Okay, part C. Whoa, n plus 1 choose r equals n. Okay, n plus 1 choose r equals n choose r plus n choose r minus 1. Okay, that's a lot. I think I have to work both sides of this because even I don't know how it's going to work itself out. But n plus 1 choose r would be n plus 1 factorial over r factorial times n plus 1 minus r factorial. Okay, there's some unpacking to do here, and I got to figure out what it's going to be. Now, on this side, I know that that's n factorial over, I think I have to get a common denominator here, r factorial times n minus r factorial. And then we have plus, did we see this before, r minus 1? We did not. We saw n minus r. N factorial over, oh boy, r minus 1 factorial times n minus r minus 1 factorial. Okay, there's a lot to do with this one. I don't think this is going to be a small problem at all. I'm curious where I want to go. One thing I want to do with the top part, because you notice this one doesn't have any n plus 1s here. So what I specifically want to do here, if you understand that, like this, right? 6 plus 1 factorial, yes, that's 7 factorial, right? But it's also 7 times 6 factorial. That the 6 plus 1 of it all, the n plus 1, is just 7. So n plus 1 times n factorial can also be written. And I write that because I think that'll help me. Maybe it'll even cancel an n plus 1 on the bottom. N plus 1 factorial is also n plus 1 times n factorial. I don't want parentheses here. Times n factorial. That's the top guy rewritten in a different way. And literally, I just used blue for some reason. On the bottom, I'm wondering if there's something similar I can do inside here. I have n, I'm going to rewrite it as n minus r plus 1. I kind of want a different version of it. In fact, I might leave it like that because I think this will turn into that as well. So I don't really know how this is going to work yet. Let's just keep going. On this side, I'm inclined to look for a common denominator. And I don't know where I'm going to go with this yet. This is n factorial over r factorial times n minus r factorial. I still don't think I can really change anything on that part. On the next part, I think I need more room. I don't know what I'm going to do yet. I want to distribute that thing. So n factorial over r minus 1 factorial. I feel like I'm going to do something with the r and r minus 1 in a second. I'll show you. Times, now distribute the negative. It becomes n minus r plus 1. So n minus r plus 1. Oh, factorial. That barely squeezes in. Let's squeeze it in. Let's get it. Okay. Now, I do want to rewrite something over here suddenly. Because this one doesn't have... Hold on. N minus r plus 1 factorial. Ooh, that's a lot. I do want to... I'm going to work toward a common denominator because clearly this has one, right? And I don't know if I can work it out in such a way that's going to make it look exactly like that. I'm going to keep this the same way. I don't think there's anything else I can change there. Maybe the n plus 1. Maybe there's something I can cancel out here. I'll explore that in just a moment. Right now, what I'm exploring here, I want to rewrite r factorial as r times r minus 1 factorial, because then I can at least share these the same way. And I'm wondering if the n minus r plus 1 factorial, that's why I'm looking at this. I feel like I can rewrite those the same way as well. So this, I'm going to turn into that in just a moment. So I'm going to do that. On this side, I'm really looking at getting rid of this n plus 1 somehow. Or if it's n minus r plus 1, it should be the same thing as before, right? It should be n plus 1. It's one more than, oh, hold on. n minus r plus 1 factorial is n minus r plus 1. That's one more than n minus r. So I can turn it into this. This can turn into that. How does that help me? I'm still working that out. Because this has the same thing. This has an n minus r factorial. I think that will help me out. But I got to figure out n minus r plus 1 still. N minus r plus 1. Okay, this is a lot. I didn't anticipate a problem like this. I still haven't remedied the n plus 1 yet. We'll figure that out when the time comes. N plus 1 times n factorial over. I have r factorial times n minus r plus 1 times n minus r factorial. And on the other side, I have, I'm going to go for a common denominator, but I have to rewrite now kind of what I do have. N factorial over, I'm changing r factorial. Oh, do I want to change r factorial? Well, I have that r minus 1. Only reason I might not want to is this still has r factorial. I only want to do it for now just because I have the r minus 1 factorial and I want to get a common denominator. We'll see if I still want that ultimately. Times n minus r factorial. And then on here, that's still a plus. This n factorial over, I need to write this smaller somehow. I know grouping it will do that to it. Let's see. Sorry that it's going to thicken this stuff a little bit, but I just need to fit this the right way. N factorial over, I have r minus 1 factorial, and then, how did I rewrite this one? N minus r plus 1. I might be going down the wrong road on this thing. If I am, I will edit, erase, and just redo what I want to do. I'll have to think about it if I have to do it more. As far as common denominator goes, notice how this is the same in both, this is the same in both over here, and this one needs a multiple of r times r over r, and this one needs r, n minus r plus 1, and on bottom needs n minus r plus 1. So I'm going to leave the other off to the side for now. Let's just look at this right side. I'm going to now write in blue. I'll have n factorial times n minus r plus 1 plus n factorial times r. Oh, I think this is going to work. I see something I want to do with this. I'll put some parentheses for now. On bottom, I have r minus 1 factorial, n minus r factorial. I'm going to write the other one first. N minus r plus 1. Now, I don't know if I want the long way for it. That's the only thing. I don't know if I want the long way to do this. But I'm seeing providence. I'm seeing the home stretch. N factorial is a common factor on top. If I factor out n factorial from the top, I'm left with n minus r plus 1 here plus r. I know people are going to have trouble with that factoring business and saying, well, how'd you do that? It's a common factor. It's like if I have xy plus xz, I factor out x and I'm left with y plus z. This is what happened here. I factored out n factorial here, just like x, and inside left is y and z. That and that. is left inside. Okay? I'm reaching the bottom of my own page here. So that's on top. On bottom, here's where I get to do some merging. Remember what r times r minus 1 factorial is? R times r minus 1 factorial, that's r factorial. That's r factorial. So I can rewrite this like that. So this becomes that. And n minus r plus 1 factorial is 1 more than n minus r factorial. Therefore, this is going to be n minus r plus 1 factorial. So I'm almost there. How am I almost there? Negative r plus r is 0. They cancel. You're just left with n plus 1. So now I have... Oh, I can probably put these back together. Did I separate those? I did. I'm going to bring those back together as well. So I'm bringing this whole thing down. I think this is kind of the last step unless there's a way to rewrite this in a cleaner way. Oh, there probably is. Just give me 1 second. N plus 1... Well, I'll do it together. But n plus 1 times n factorial, because I think I split that up as well. Didn't I? Yeah, I split up n plus 1 factorial into that. Maybe I didn't really need to touch this side. Maybe if but I think using these ideas made me understand how they'd work, so I probably had to in my head. But maybe I didn't have to touch that side, but I am going to bring that back. But I have n plus 1 times n factorial on top still, which I will clean that up to n plus 1 factorial. And on bottom, I have r factorial times, and like I said, I'll bring this back to n minus r plus 1 factorial. Can you still see all that? Yeah. And then over here, I have equals. I have n factorial, and like I said, the r's canceled, so now I just have n plus 1 there. And then on bottom, I also have r factorial times n minus r plus 1 factorial. So although I kind of ran out of space, I'm sorry about that thing kind of showing up. I should have formatted that better. N plus 1 times n factorial, that's 1 more than n factorial, which is n plus 1 factorial. And on bottom, I still have this. I don't know if this part can clean up. I don't think it can. I'm just going to leave that as n minus r plus 1 factorial like that. And this side has the same merger. N factorial times n plus 1, that's n plus 1 factorial over that guy. So like I said, was that the initial setup of the left side of this problem? We'll check it out, because if it is, then I feel like I'm in the right sense for that. N plus 1 factorial over r factorial. Yes, it was. So it took cleaning up this side, but I think I needed to make sense of why it would clean up to that for it to make it happen. I'm sure they might say n plus 1 minus r factorial. Maybe I should leave it like that. N plus 1 minus r factorial. Okay, and I don't think it can clean up more than that. I don't think you can do anything like cancel these out. I don't think that really works in that way. So I know it doesn't. I just don't know how to explain that. So yes, that all works out. We're all good that these are indeed the same. That was quite a bit, quite the ordeal, and we are set. That was a very long problem just on that 142C. Again, I might have gone a slow way on it, and I was discovering. But discover I did. I got there. I'm going to drink water after all that. Number 43. Complete the table for each given value of r. Then write an inequality relating NPR and NCR. Explain your reasoning. All right, I'm going to copy that table. Let's copy that over. Let's see. I think I have to sneeze. Okay, so we have this. If r equals 0, 1, 2, and 3. So basically here, we're doing 3 pick 0, 3 pick 1, etc. And say with 3 choose 0, 3 choose 1, like that. So 3 pick 0 is 3 factorial over 0 minus 3 factorial. So 3 factorial, that's 1. 3 pick 1 is 3 factorial over 2 factorial. So that's 6 over 2. Excuse me, 3, it's 3, it's 3. So 1 and 3. 3 pick 2 is 3 factorial over 1 factorial. So that's 6 over 1, which is 6. And then 3 pick 3 is 3 factorial. Wait, I think, right? 3 pick 3, I mean it is. But 3 factorial over 0 factorial. 0 factorial is 1, and you still get 6 with that one as well. So 1, 3, 6, 6 are those values. Now, I know this is 1, 3, 3, 1, because I just know how these ones work. I'm thinking of Pascal's triangle, if you heard me talk about that earlier. But this is, it says complete the table. It doesn't say how to do it. So we could use the calculator. Listen, we could use the calculator, but I'll just write this one out. 3 factorial over 0 factorial times 3 factorial. And I mean, it still works itself out that way. What do they want to say? Write an inequality relating NPR and NCR. Explain your reasoning. Well, I've already said this several times here, but as you notice, as this thing grows, you can see that the pick formula thing starts to increase over time. This one has symmetry to it, and it decreases. But the pick is always at least equal to, if not greater than, this. I'm sure that's a conjecture. But, yeah, NPR, I'm just going to write it like this. NPR, actually, I can do subscripts. NPR is greater than or equal to, which I believe I have that symbol somewhere. Greater than, there it is, greater than or equal to NCR for no matter what you have. Explanation, I mean, as far as explanation goes, you know, we're using the table to support our claim, but it doesn't explain it. The explanation is you have the same number of arrangements regardless, but in one order matters and the other doesn't. All things being equal, meaning same set you're choosing from, same set and number of choices, or arrangements, I'll say, number of selections. Order matters for permutations, so you don't neglect the duplicates. They'll never be less than their combination counterpart. So, you know, when you look at the formula itself, the whole n, I mean, there are other ways we can talk about it, right? This formula is n factorial over n minus r factorial. This one's the exact same thing, but there's something else that's being divided. Another r factorial is being divided there, right? So if r needs to be 0 or greater as a value, if r must be 0 or greater as a value, and 0 factorial is 1, 1 factorial is 1, after that, 2, 3, 4, 5, those are numbers bigger than 1, you're always going to be dividing by something more, 1 or more, which means it's going to get to that as well. But there's the inequality, there's the setup, it's all good. All right, number 44, write an equation that relates NPR and NCR. Well, I sort of just did right here. I don't know if that counts. Well, that's not an equation. Then use your equation to find and interpret the value of this over that. That relates them. Can I just use the division they're doing here? Can I say that relates them? Can I use, okay, how about this? NPR, okay, if you notice, I just wrote this up top. NPR, you have to take your NCR equation and multiply by r factorial, right? To make this match that one, they need to, for them to be the same, this needs to be r factorial times bigger in that way. So when we're doing 182 pick 4 over 182 choose 4, that'll be, oh, so hold on. If that's the equation that relates them, then let's do this. Let's divide both sides by NCR. How about that? Because then we can make it look the same. So now r factorial equals NPR over NCR. Great. So when I do this, r factorial is NPR over NCR, 182 pick 4 over 182 choose 4 should be 4 factorial. And 4 factorial is 24. That should be it based on what we're kind of doing there, that they relate with the r factorial bits on number 44. Okay, number 45. You and your friend are in the studio audience of a television game show. From an audience of 300 people, 2 people are randomly selected as contestants. Sorry, 2 people. What did I say? Did I say 3? 2 people are randomly selected as contestants. What's the probability you and your friend are chosen? Very low. Order doesn't matter. If you and your friend are chosen, it's either you and your friend or your friend and you. That's still one kind of choice. In that way, it asks for probability. So probability you and your friend are chosen. You and friend chosen. what we have to do is think about the number of different ways that you and your friend can be chosen. That's one. There's only one way you and your friend can be chosen if you're both chosen. How many different ways can anyone else be chosen? There are 300 people and 2 that are chosen. With that, where order doesn't matter, looks like that. 1 over 300 choose 2. This is where I'm more inclined to just go to the calculator. Whether or not it's an easy number to do, I just want to kind of, the talking through it is the important part, and then doing everything after that's just kind of the work. So I'm going to get, I got 44,000, where is it? 44,850. So the probability is 1 over 44,850. That's the and this is one where, like I said, there's no reason to write the decimal or the percentage. It's a very small number. It's less than 1%. It's close to 0% odds. You're not letting it happen. So writing the fraction is just fine. And I think they did it in the examples as well. Okay, number 46. You work 5 evenings each week at a bookstore. Your supervisor assigns you 5 evenings at a random from 7 possibilities. Yeah, 7 days in the week, right? What is the probability your schedule does not include working on the weekend? Well, probability of not weekend. Weekend is 2 of the 7 days. The weekdays are Monday through Friday. That's 5 of the 7 days. The only way it's possible you don't work on the weekend is if you work Monday through Friday. This is also a combination set because it's you working those days. I mean, the order is the order, Monday, Tuesday, Wednesday, Thursday, Friday. There's only one way you cannot work on the weekends. It's if you just work on the weekdays. But there are different ways you can arrange how to work in the week. 7 days in the week, you choose 5 of them. Again, order doesn't matter. Sunday, Monday, Monday, Sunday, it's still those 2 days. So 1 over 7, choose 5. I believe we've done 7, choose 5 before, but I'm going to let my calculator work it out anyway. 7, choose 5 is 21. So 1 over 21, which, look, that's not a tiny number. That's a little less than 5%. But we're going to leave them as fractions as long as it seems like everything should be written as a fraction there. All right, in exercises 47 and 48, find the probability of winning a lottery using the given rules. Assume the lottery numbers are selected at random. Does order matter in a lottery? Oh, they literally say order is not important, order is important. There we go. You must correctly select 6 numbers, each an integer from 0 to 49. The order is not important. Order is not important means combination. Okay, did they say probability? Yes, probability. So the number of possible ways you can do that numbers can be chosen, right, is from 0 to 49. By the way, don't be fooled. From 0 to 49 is not 49 numbers. It's 50 numbers. 50 numbers, and we're trying to choose 6 of them. Order doesn't matter. So in that case, in the 50 choose 6 set, we're doing 1 out of, right? 1 out of certain amount. So order doesn't matter. 1 out of the 50 choose 6. Now 50 choose 6. 50 choose 6 is big number. Big number. 15 million. Hold on. I just lost it. 15,890,700. So even though order doesn't matter, that's still huge. All right, there's the probability. Number 48, you must correctly select 4 numbers, each an integer from 0 through 9. Order is important. Yeah, if they did the same probability thing for order, I just forget it. Already here, forget it. But, correctly select 4 numbers, each an integer from 0 to 9. So from 0 to 9, remember, that's 10 numbers. So order important. Remember, this is 10. Pick 4 on the bottom here. But on top, you must correctly select 4 numbers. You have to make sure you do it in that exact order. So as I'm working out 10 pick 4, I'm getting 50 40. There's only one way that you got to get that one right out of the 50 40. So 1 out of 50 40 is your probability there. If it's the numbers from 0 to 9, it's 7902, right? You must exactly select 7902. There's just one way out of the 50 40 that you get. Small, but a better lottery chance than that. I like them odds better. That sounds strange, but it doesn't when you do the math. Number 49, I think we have 10 problems to go. A polygon is convex when no line that contains the side of a polygon contains a point in the interior of the polygon. Basically, it's something, it's when they don't go inward. So like here's like a heptagon or whatever. A different version of a heptagon that wouldn't be convex is something like this one, where I got to erase the other part. I don't know how to cleanly or quickly. Sorry. This is an example of a polygon that wouldn't be convex, right? It's still a heptagon, but suddenly a diagonal can be drawn on the outside of it. What color they use? Red. Here's a diagonal drawn on the outside. It's no longer convex. So that's not what they're talking about. They're talking about these ones like this. Anyway, what do they want to know? Consider a convex polygon with n sides, like that pentagon you see there. Use the combinations formula to write an expression for the number of diagonals in an n-sided polygon. All of them? I was thinking of n minus 2, like the triangle formula. Okay, well, a pentagon... Ooh, I don't know. Okay, well, here, let's think about this. A triangle doesn't have any diagonals. A square... Did they say number of diagonals? A square has 2. I'll draw them in a second. I'm just getting a few of these. I'm going to do 3, 4, 5, and 6 and see if I can see a pattern. A triangle has 0 diagonals. A quadrilateral has 1, or has 2. A pentagon, well, you can draw a star. It has 5. A hexagon. Even if I come up with an answer in this kind of way, did I do all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, what's nice about that is I just noticed how I counted those out. I'm counting out 1. I'm counting out 2 less than the number of... Oh, shoot. Let's see. How do I say that? There were 6 sides here, but as this branches 1 and 2, because I'm from a vertex, so I could branch out 5 different ways, but I'm only actually going to branch out 2 less ways, right? I could branch out 5 ways because these vertices are not diagonals. So I can only branch out 3 ways from each thing, and then I'm multiplying by the number of sides there are. Like this pentagon. There are 5 sides, and from each set I'm branching out 2 parts. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And why is it 1, 2? Because from any vertex there are 4 different... Oh, that's how it works as a combination. There are 4 different... let's see how I write it as a combination. But there are 4 different vertices I can go to from a vertex, but only 2 of them, or only 2 less of them, are diagonals. What do they want? Probability? Combination formula to write an expression for the number of diagonals inside a polygon. So let's see if I can think that out. If I have n sides, it's less about the sides for me. I'm thinking more about the vertices. N sides is n vertices. Well, I do think about sides because I think about vertices. With each vertex, I'm branching out there and I multiply by the number of vertices. So I can multiply the number of vertices times the number of... How do I say this? The number of ways I can draw a diagonal from any vertex. So in the case of 3... I can do 0 of them because it's 2 less than the number of ways I can branch out from there. From here, I can branch out 1, 2, 3 ways, but I'm doing 1 less than that. Is that n minus 3? Did this say combination? Yeah. For 5, hold on. 5 choose... Well, here's the cool part. Whether I do 5 minus something or that number, it's still going to work out. There are 2... Oh, how about this? There are 2 less than the number of sides there are I'm branching from. No. Is there 3 or 2? 1, 2, 3, 4 vertices and choose the 2. There are 2 less than that. Let me first work out... Well, 5 choose 2 and 5 choose 3 are the same thing. But here, let's go to 6. What did I say for 6? There are 15 of them. 6 choose... I really have to think about this one. 6 choose 3. 6 choose 3. Is that how I'm saying it? 2 less. Oh, 2 less would be 6 choose 4. 6 choose 4. I have 6 vertices to choose from. I have 2 less than it. So that's 6 factorial over 4 factorial times 6 minus 4 factorial, which is 720. Excuse me. Let's do it in the faster way, right? 2 factorial. That's 6 times 5 over 2 times 1, and that's 15. So that worked. Does that work for the other ones? 5 choose, I guess 3, because 2 less than the number of things there are. That's 5 factorial over 3 factorial times 2 factorial. So that's 5 times 4 over 2 times 1. That's 10. Oh, this isn't 5. This is 1, 2, 3, 4. Wait, is it number of diagonals? Oh, that's a duplicate. Hold on. 1, 2, 3, 4, 5. Oh, this might not be 15 then. Use the combinations number of diagonals in inside of. Oh, this might not be 15 then. So hold on, because I was counting from a thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and that's just 9. Then maybe it's not. Maybe it's not that then. Because that was just 2, right? It's not like I double up on what I have. Let me think about that then more. Let me pause and think about that. We'll tell you what, I didn't have to think about it long. I started to go back to why was I doing n times something? That's because I was starting to branch out from something here. And then like this one times 5 because there are other ones. But I don't think I want to do an n times something. Rather, we use our, because I think I still like what I'm doing here, the 15 different ways that you can arrange all those things there, but we take out duplicates. Now, duplicates come in the form of however many sides there are. If there are 6 sides, then we take out 1 here that would have been overlap of this one, and 1 here that would have been overlap of that one, and there's 1 for each side that can be removed. So I think we would take out 6, the number of sides, and that's where we get the 9 from. So instead of 15 here, we say 9. And I think that applies to these ones, right? Because if this other one would have been that number, which is 10, 5 factorial, 20 over 2 is 10, we subtract the duplicates of everything, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But each one was doubled up. We remove 1 from this side and 1 from this side and 1, because there's overlap. You know, there's overlap there. So 10 minus 5. So I think your formula would then be n. I guess 4 works as n minus 2. So you take your number of sides and you choose n minus 2 of them, like that, or 2. You're going to get the same number. And then you subtract n from it. I want to see if that works for the other ones. 3 over, or 3 choose 1. 3 choose 1 is 3. Minus 3 is 0. 4 choose 2 is 24 over 4 is 6. And 6 minus 4 is 2. Yeah, that seems to work for me there. I don't know if I can re-explain it. I processed through it and got to it. But that's what I'm using. That's kind of a hard problem. That was part A. Part B. Use the result from part A to write a formula for the number of diagonals of an n-sided convex polygon. I just did. Oh, one's a combinations formula, the other is a formula. So I guess I just keep going. So here, this equals, I think, n factorial. I was hoping they were just going to say for a 10-sided polygon, and I'd be on my way. But n factorial over n minus 2 factorial times n minus 2 factorial minus n. Okay, this is kind of going to be like that part C question, only I think this is going to be easier, but I got to get a common denominator eventually. So n factorial over n minus 2 factorial times so this negative distributes here. N minus n is 0, minus negative 2 is plus 2. So that's 2 factorial here. And that's minus n. Now, before I get a common denominator, let's clean up what's here. Right, 2 factorial is 2. And n factorial, see, check this out. N factorial is, whoops. N factorial is n times n minus 1 times n minus 2 times n minus 3 times all the way to, 1. But that means n minus 2 factorial shows up there. And if n minus 2 factorial is down here as well, then those can cancel out. So here I just have n times n minus 1 on top and 2 on bottom. Whoopsie. And that's minus n right here. So I have n times n minus 1 over 2 minus n. And I can multiply this by 2 over 2 to get a common denominator. So now I'll have n times n minus 1 minus n all over 2. That's a version of the formula, but I think it can probably clean up more. To n squared minus n, whoops, all over 2, which is n squared minus 2n over 2, or n times n minus 2 all over 2. That's what I'm going with, and that's a much better version of what I wrote than before. And I feel like, honestly, and not that I could have gone the other way with that thing, but I feel like that's a better version of what I could have gotten to before all was said and done on that thing. Oh, hold on a second. That wasn't, this is a 2n for common denominator. That means this is 2n. That means this is 3n. There we go. And minus 3. What was the point I was making? Oh, yeah. I think I could have gotten to this answer better myself from that top part than the combination one. And this one actually probably works the way I was talking about it, where I was saying that you have n sides or n vertices, and you can branch out to your diagonals 3 less ways than what you have, because from there, 2 vertices aren't going to count on the sides. And then that vertex you're on doesn't count, and everything else is diagonal there, and you multiply by the number of sides, but you divide by 2 to ignore all the duplicates that are there. I think I get that part of the formula better than the other one. I think I do, but there it is. N times n minus 3 over 2. That's what I'm going with. I hope it's right. The way I talked through it seemed to make sense. Okay, number 50. You're ordering a burrito with 2 main ingredients and 3 main toppings. The menu below shows the possible choices. So that there are 6 main ingredients and 8 toppings. How many different burritos are possible? Yeah, so when it comes to arrangement things here, we are going to multiply whatever our arrangement of number of main ingredients are by toppings. I don't know if that's obvious. I don't know if we've done that in such a way that makes sense. But for the main ingredients, order shouldn't matter. Chicken and rice, rice and chicken, it's the same thing, right? So I can do 6 choose 2, 6 different choices, and I'm going to select 2 of them. And I'm going to multiply that by 8 choose 3. 8 choose 3. It's not a probability question, right? How many burritos are possible? A lot. There are a lot of them. I'm using the calculator for some of this stuff. I can do it straight up, but I also want to do them not straight up, if that makes sense. 6 choose 2 is 15. 15 different main ingredient arrangements, and then multiply that by 8 choose 3. The 56 different, what do they call them, toppings or whatever? 56 different topping ingredients, y'all, and 15 times 56 will be the ultimate result, which is 840. 840 different burrito arrangements. Ain't that crazy? You could literally go every year or every day in the year, and that it'll still take more than 2 years to do all that. Then someone could tell me what the best arrangement. Isn't that weird that if someone said, hey, what's the best one to recommend, you literally wouldn't know until you've tried it 840 times. That's crazy. And it just goes to show how we kind of marry to certain things, because I'm not going to try 840 different combinations. Okay. Number 51. You want to purchase 2 different types of contemporary music CDs and 1 classical music CD from the music collection shown. How many different sets of music types can you choose for your purchase? I think it's a lot like number 50. We see our list. There are 5 different contemporary sets to choose from. Honestly, wouldn't be able to tell you what genres were contemporary if I knew. But you want to purchase 2 different types of contemporary music. Still a combination. Order doesn't matter. And 1 classical music CD. So we're going to do 5 different options. Choose 2 of them. Times That's a 3 choose 1. So this time, I should know 5 choose 2. I think we just did it. Wasn't it like 20 or 10 or something? I think it was 10. 5 choose 2 is 10. I know that 3 choose 1 is 3. So 5 choose 2 is 10. This times 3. There are 30 different sets. I'm going to say sets. I don't know if the other said ways, but I'm going to say sets for that. All right, number 52, asking how do you see it? A bag contains 1 green marble, 1 red marble, and 1 blue marble. The diagram shows the possible outcomes of randomly drawing 3 marbles from the bag without replacement. So when you pick the marble out, you don't put it back in. So the first draw, if I draw green, then I could draw blue then or red then blue, or blue then red, etc., etc. How many combinations of 3 marbles can be drawn from the bag? Explain. Well, if order doesn't matter, this is number 52. If order doesn't matter, there's one way to do it. 1. I'll write the number. 1. I mean, as far as combination stuff goes, my explanation is it's 3 choose 3. You have 3 marbles. You're going to choose all 3 of them. It doesn't matter. All of these things in terms of combination are the same arrangement. You chose green, red, blue, or blue, green, red. Great. That's the same 3 marbles. That's all that matters in a combination. Order doesn't matter. Part B, how many permutations of 3 marbles can be drawn from the bag? Explain. Well, this time I'll show the work first. That's 3 pick 3. I mean, I can count them. They go from here. Green, red, blue, red. Those are 2 different ones. Red, green, blue, green, blue, green, red, green. That's 6. 1, 2, 3, 4, 5, 6. And that should be explained through 3 pick 3, which, by the way, is also 3 factorials we've seen, or 3 times 2 times 1, which is 6. So that's part A. Part B on number 52. Almost done. 6 more questions. Number 53. Every student in your history class is required to present a project in front of the class. Each day, 4 students make their presentations in an order chosen at random by the teacher. 53. You make your presentation on the first day. Each day okay, so the first day part doesn't matter. It's just they ask first day on both of them. Okay, yeah, the first day part doesn't really matter. But 4 students are chosen at random. They don't say how many students there are. What's the probability you're chosen to be the first or second presenter on the first? Okay, it says you're chosen on the first day. So given you're chosen on the first day out of 4 students, the question's there. What's the probability you're chosen to be the first or second presenter on the first day? First or second. Probability of first should be same as probability of second. So it's this plus that, I'd say. You have a 1/4 chance of being chosen first, right? I'm trying to think of how to write it as a permutation kind of thing. I kind of want to just skip the permutation part. You are the 1 probability of first presenter. It's you being first out of 4 different possibilities of being first. Probability of second. Sorry if I'm not going to write this as an actual permutation kind of thing. Probability of being second, it's you out of 4. It's still 4, right? 4 different presenters, yeah. This isn't given that someone was chosen first. It's just it's a random drawing. Okay, Bob, Jake, whatever. So probability of first or second. I just wrote out 2. Is 1/4 plus 1/4. There's no overlap there. That's 2/4, which is 1/2. Sorry if I didn't get that in a permutation kind of way. I don't want to make a mistake, so I'm just going to leave it as that. I mean, I guess it still works regardless of how we say it. So, there it is. Okay, let's go to number, that was part A. Part B. What's the probability you're chosen to be second or third presenter? That shouldn't change. Third is still, probability of being third is still 1/4. So probability of second or third is still 1/4 plus 1/4. It's not going to change. So they say compare them. Same. Same. Boom, 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 boom. Sorry about that. All right. Let's go to number 54. The organizer of a cast party for a drama club asks each of the 6 cast members to bring one food item from a list of 10 items. Assuming each member randomly chooses a food item to bring, what's the probability at least 2 of the 6 cast members bring the same item? Oh. So two of the 6, well, at least 2 of the 6, 2, 3, 4, 5, or 6, means anything but what's the probability of bringing unique items. So probability at least 2 is 1 minus the probability of each unique. So I'm going to find the probability of everyone bringing a unique item and subtract 1 from that. That's what, actually, now that I look at this problem, because I don't know if this combination permutation, what I want to say there, but it almost seems like these questions, because this was after what, the how do you see it thing, looks like these are kind of intermixing with the previous things from before. This or part did an addition of things. I don't know how I was going to use combination permutation, probably a very easy way. But here, the at least thing, the 1 minus the complement, it seems like we're using kind of other things now. So probability of unique. How many different ways can people bring items in general? They don't have to be unique in the things. What if everyone brought the same item? What is it? Bring one food item. What if everyone brought salad? I mean, there are 10 items. What if everyone brought that one item? So probability of unique, it's possible that everyone can bring the same one item. Everyone can bring the same one item. There's six cast members. So this cast member could choose from 10. This cast member could choose from 10. That's 10 to the 6th power. That's out of how many there could be. That's a million. In a unique set, we need to make sure that everyone brings something unique. And how many different ways can we each bring a unique item? That, I guess that's a permutation, but I was thinking of saying 10 times 9 times 8 times for 6 slots. So I believe that'd be 10 pick 6 on top. I think that's how many different unique ways can we arrange unique items. So I believe that's what that is. I don't know what that is a fraction. Let's do that. I have to drink water. Let me just divide them. Let's see. 151200 over. Hopefully I can reduce that. I mean, I can. Hopefully my calculator can reduce for me. Okay, this reduced to 189 out of 1250. So that's the probability of a unique set. Probability of at least 2 is 1 minus probability of unique. So probability of at least 2, we're looking at 1 minus that. So I need to do 1250 minus 189 for a common denominator. That's almost a good problem to write a percentage for. 1061. So 1061 out of 1250. I want to see what that percentage is. 1250 is 0.8488, so 84.88%. There's a high probability that someone's going to bring the same item as you. There's a low, actually I expect it to be higher. There's about a 15% chance that you guys are going to bring uniquely different items and that. All right, number 55. You are one of 10 students performing in a school talent show. The order of the performances is determined at random. The first 5 performers go on stage before the intermission. These kinds of problems mess me up. I don't know if I'll get it right. Because now they're talking about intermission. There's a part. What's the probability you are the last performer before the intermission and your rival performs immediately before you? There are kind of 2 ways we can, I did this in I forget if it was the lecture or not, but I kind of dropped in and said it doesn't matter what the arrangements of the other people are because they're just going to be whatever they are regardless. We're really looking in those 2 slots. So to me, I'm saying the probability that it's going to work out that it's you in this slot and him in this slot, or your rival, is there's one way. There's one way in those 2 slots that's going to happen. Among those 2 slots, how many different ways can those 10 be chosen? There are 10 times 9. Now, I know that's not written as a permutation, but what I'm really saying there is 2 pick 2. Wait. Is that 2 pick 2? Maybe it's not 2 pick 2. Maybe it's 1, whatever. Out of 10 pick 2. I can say it as 1. Let me move this thing over. This is one way that you and this dude can be chosen out of 10 pick 2. That'll be the 1 over 10 factorial over... See, I don't want to do a fraction within a fraction. Of course, I could have done that first. 10 factorial over 8 factorial. So 1 out of 90, I'm going to say for that one on part A. Shoot, it's part A. I always keep hoping I'm just moving forward and not having to do a part A and B. Part B... I just lost. Okay, part B. What is the probability you are not the first performer? Well, what's the probability you are the first performer? Probability of not first is 1 minus probability you are first. What's the probability you're first? 1 out of 10. So 1 minus 1 out of 10 is 9 out of 10. I don't really know what else to say on that problem. I'm not doing combination permutation stuff. It's just, that's it. We could answer that well beforehand. So it's kind of a review. They're asking you to do different things. All right, number 56. How many integers greater than 999 but not greater than 4,000, so between 1,000 and 4,000 inclusive, can be formed with the digits 0, 1, 2, 3, and 4? Repetition of digits is allowed. All right, so between I'm going to have to write some of these out and think about it. So I have 1,000, 1,001. If this is me processing, this correctly, I could do that. I can't do 1,005 because I can't use the numbers. I can't use the number 5. After this, I could change the 0 to a 1 here. So 1,010, 1,011. I'm not going to literally write everything out. I want to come up with a pattern. 1,012, 1,013, 1,014, and then I move to 1,020. So from this set, before I move on to my next tens digit, there are 5 of them. 5 of them, and then another set of 5, and we can keep doing that until 1,040. So the 1,020, 1,030, 1,040, and among them there should still be 5 and 5 and 5. After those sets, we got to move to the 2,000s. So, okay, so that's 25. After that, we got to move to the 2,000s and the 3,000s and the 4,000s. No, it stops at 4,000. So 2,000s, I don't think there's any difference in how that works. 2000, 2001, 2002, that works in the 5 times 5 realm as well, all the way to 2040 something. So 5 dot 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 dot, and then 3,000s is the same thing. So it's 25 in each of them. Wait. 25, 25, 25. Wait. Right? Oh, hold on a second. There are hundreds. There are hundreds of these things as well. And that's another 5. 0, 1, 2, 3, 4. That's another times 5. So 25 times 5 is 125. And then there are 3 sets of them. Times 3 is 375. Sorry, the way that I'm thinking, I'm trying to just come up with it in a natural way. So, okay, so here's what we're doing. We're doing 5 numbers for the ones digit. Oh, that's easy to say. 5 for the ones digit. 5 for the tens digit. 5 for the hundreds digit. 1,000, 2,000, 3,000. 3 for the thousands digit. That's for the 1,000, 2,000, 3,000 slot. And there's the number 4,000. 4,000. That's just 1. So 125, 375 plus 376 There should be 376 different ways for that. I probably should have worked that. And I probably should write this the other way, right? It should be 3 for the thousands place, 5 for the hundreds, 5 for the tens, 5 for the ones, plus an extra 1 after that. So that's how I'll write that there. That was actually easier than I made it out to be working that out. All right. 2 more questions. Number 57. There are 30 students in your class. Your science teacher chooses 5 students at random to complete a group project. Find the probability you and your 2 best friends in the science class are chosen to work in the group. Explain how you found your answer. 57. Let's first come up with all the different ways that you can make groups, right? 30 students in your class, your science teacher 5 students are random to complete. So there are 30, choose 5. The order shouldn't matter here, whether it's, you and whatever. You're in the same group no matter how you're chosen. So 30, choose 5 is the total. You and your 2 best friends are science class. This is one where, you and your 2 best friends are grouped together. Like you want to treat yourselves like one set. You guys need to marry together in a set. So, when we do the arrangement set things here, we would do, how do I think about it? I'm thinking about it, sorry. It's not 5 choose 3. You're not saying how many different ways in the group can you and your friends be arranged. It's how many different ways can you and your friends be arranged. Oh, hold on. That says the same thing. In a group of 5. But the thing is, the other 2 people can be anybody else. So how about it's like this? You and your friends are just one set of people, but I'm going to set you as 3 different people. 1 times 1 times 1. It's not like 30 times 29 times 28. But the others are. The others are 27 and 26. Like that. There are 27 different people who could be chosen with you. There are 27 different people who can be chosen with you in this slot, and 26 different people who can be chosen with you in the second slot after you, your friends, and stuff are chosen. The question is, but order shouldn't matter, so you shouldn't flip-flop them, so you should be dividing by 2. So I think that's 27 choose 2. Not 27 pick 2. Order doesn't matter. It shouldn't. On top if it doesn't on bottom. That's all divided by 2 because you don't want overlap of, like, if it's Kate and Taylor or Taylor and Kate, we can swap it. No. You divide that by 2 there. So I think it's 27 choose 2 over 30 choose 5. And that is, I'm going straight to the calculator for that. I'll write the fraction, though. 27 choose 2, because maybe we can reduce it. That's 351 over 30 choose 5. 30 choose 5 is, 142,506. Let's see how this reduces. 351 divided by the previous answer, and write as a fraction, 1 over 406. 1 over 406. Very small possibility here, but it's possible. We just got to see if it can actually, work itself out. Now, how did I get that? The number of groups, well, I explained it. But the 27 choose 2 is the number of way that you and your friends can be arranged in a group, because you and your friends are treated as this set, but then there are 27 other students that can go into your groups and be arranged in that. And that's among the 30 choose 5 that we have. So that's the way I'm processing that. I'm thinking I'm getting the answers right. I just can't guarantee if I can explain it in the best way. All right, last question, number 58, problem solving. Follow the steps below to explore a famous probability problem called the birthday problem. Assume there are 365 equally likely birthdays possible. And apparently that's not the case, right? I think there's something where people are more likely to want to have babies and stuff like that. Not just want to have them, but when they'll... All right. What's the probability at least 2 people share the same birthday in a group of 6 randomly chosen people and in a group of 10 randomly chosen people? So there are 2 questions in one there. That's That's great. Thank you for doing that. At least 2 people share the same birthday. Well, aren't we referring to then... Okay, because I think everybody can have the same... Anyone can have any birthday. They said out of 6 randomly chosen people. So, probability of... I don't know if I want to write the probability part, because I just want to work this thing out. If any one person can have any one birthday, the total number of combinations is 365 to the 6th power. It's like the same one with the cast members choosing food items there. And actually, this is just like that, because after that, we can say this is 365 pick 6 from that set, because that's the 365 times 364 times 360, like that kind of scenario. So that would be the number of ways that you can choose. Those are the number of unique... Sorry, that's the probability everyone has a unique birthday. Everyone has a unique birthday, because first person would have 365 options, next person has 364, and so on. So actually, I want to do 1 minus that. I want to do 1 minus that result, and then that would be my probability. Now, I don't know if I can write that as a fraction, but 365 pick 6. Well, it's a big number, but 365 to the 5th to the 6th is even bigger. So it's a high probability you'll have unique birthdays. And this isn't simplifying as a fraction, so I'm just going to have to do the 1 minus. So 0.04. Actually, 0.0405. So it's around 4.05%. You have 6 people. Hey, that's funny. That's my birthday. Oh, wow. What were the odds? Or what was the probability? What were the chances? Actually, I think that's a little higher than I imagined it to be, but that seems to work out. Not part B yet. Now we have to do it for 10. So now we got to do 1 minus 365 pick 10 out of 365 to the 10th. Basically, what I'm doing here is we're doing, 365 times 364, etc. for the number of slots that there are, right? So I'm just going to do that again. But 365 pick 10 divided by 365 to the 10th and 1 minus that. When you get more people, it's more likely it's going to happen. So now this one becomes around, I'm just going to say the percentage, 11.69%. So now it's like, okay, yeah, there are greater odds now than there were before, and I think that just seems to make sense that that'll be the case. So there you have it. Okay, that's part A. Part B. Generalize the results from part A by writing a formula for the probability that at least 2 people in a group of n people share the same formula. Use NPR. Well, I just did that. So this is what I was doing. Well, I didn't do it for n and stuff, but that's what I was doing for this kind of thing, right? So in this case, they say for n, for what? Probability P of n, at least 2 people in the group share the same birthday. Would that have been P of 6 and P of 10, that there were n people? Is that what they were saying? So, okay. So here I would just do 1 minus 365 Pn, pick n, divided by 365 to the nth power. I keep writing it. Sorry about that. I guess that's it. All right, cool. Part C. Enter the formula from part B into a graphing calculator. Use the table feature to make a table of values for what group size the probability at least 2 people share the same. Okay, I want to use Desmos, not my actual graphing calculator. So give me 1 sec to pop that one up. So let's do Desmos. I never really used a permutation formula in a calculator. Let me see if this works. Let's do like f of n equals 1 minus... I don't know how to do it on Desmos. Hold on. Let me see if this pops up for you guys. Google Chrome. I have Desmos. Okay. Let me expand that a little bit here. Okay. So in Desmos, I'm doing n 1 minus 365 365. I got to see if this has the options. Functions? If this doesn't, I'll have to use my other calculator. Oh, it's right at the bottom. 365. Oh, I don't know how this works. Do I use a comma? Hold on. I don't know how this works. It's 365 comma. Some of these are weird, but like Excel, it might be a formula like that. N? Okay, at least that works. So let me get rid of the 365 here. 1 minus that over 365 to the nth power. I think that's working. Now I have to interpret, I have to come up and interpret what it is that we're talking about. So they said use a table of values, so I can use a table where I have n and f of n. Oh, I guess I need to turn this into x1 and x1 and x1. Okay, if I plug in 1... Wait, how does this work? Okay, I'm going to undo that. Okay, I could just use a graphic calculator and find where it works, but it says use a table of values. Oh, do I use n and f of n? Is that how that works? F of n? Shoot, I was hoping it would spit values out for me. And I don't know what I'm doing with that anymore. I forget how Desmos works for table values. I'm just going to plug numbers in. Like f of 1 is 0. Great. What's f of 100? Huge. What's the question? Oh, this is the probability thing. Hold on. So this is like 6 different people, right? Here's the 6 different people. Can I zoom this in? Can you see that better? Okay. 6 different people as that probability. We saw that. 10 different people as this probability. Okay, this works out. So 11, 12, 13. Let's go to 20. What did it say? When does it exceed 50%? At least 2 people share the same birthday exceed 50%. So there's 20, 21, 22, 23. So once you have 23 people in a group, there's more than 50% chance that 2 people or more are going to share the same birthday. So 23 people is the mark there. Whoops, you didn't see that on the thing. All right, that's how I'm just going to do that one. I hope that that kind of worked out. Because I'm not sure how to plug in the values of Desmos. I should, and suddenly something's not working the way I wanted to. All right, guys, that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. This was a longer one. I didn't know what to expect. But, yeah, there it is. So listen, if we got one more section here, but if you want to check out other things in the IM2 playlist, check the description section down below, and you can find them there. So, y'all, take care. Thank you. I'll see you in the next one.